In this section, we are going to discuss dynamics. So we are going to discuss forces in this video. According to Isaac Newton, or in classical physics, there are three laws of motion. Actually, those three laws are saying almost the same thing. But for the sake of understanding, we will stick to those three laws. For the sake of time, I've written those three laws, but I'm going to explain them better. So those three laws are commonly referred to as Newton's laws of motion. Now, the first law is called law of inertia, and it states that a body continues in a state of rest or of uniform motion in a straight line unless acted upon by external forces. What it means is that an object at rest will remain at rest. An object moving in uniform motion will continue in uniform motion unless an external force is applied. It means that force is an agent of change. That is the definition we are going to give to force as Newton's law is concerned. And it also means that every object that possesses a mass has inertia. So what is inertia? Inertia is reluctance of an object to change position. That is, when an object is at rest, it wants to remain at rest. And when an object is in motion, it wants to continue in uniform motion in a straight line. Now, the second law is the law of dynamics, right? And the second law states that the rate of change of linear momentum of a body is proportional to the applied force and takes place in the direction of the force. So let's look at this law closely. So the law says that the rate of change of linear momentum. So what is momentum? Momentum in physics is usually designated as P, and momentum is equal to the product of mass and velocity of an object. So this law can then be represented as the applied force F is proportional to the rate of change of linear momentum. So rate of change of linear momentum will mean change in linear momentum over time. When you have rate means over time. Which then means that we have force to be equal to change in momentum will mean final momentum minus initial momentum over time. That means we have this law to be written as constant multiplied by final momentum will be mass times final velocity. Then initial momentum will be mass times initial velocity all over time. Then we can write the law as F equal to A mass into final velocity minus initial velocity over time. If you have seen the video on linear motion, we know that acceleration is equal to final velocity minus initial velocity over time because this is change in velocity over time. That means we can then write the second law as F is equal to K multiplied by acceleration because change in velocity over time is acceleration. All we have here is equal to acceleration. If K is equal to 1, that means we can write the law as force is the product of mass and acceleration. This means that this second law can also be stated as the force applied to an object is directly proportional to the acceleration, provided that the mass remains constant. Which means that if you have a bigger mass and a smaller mass, and you apply the same force to them, right, the smaller mass is going to have a higher acceleration, while the bigger mass is going to have a smaller acceleration. So that is Newton's second law of motion. Now, the third law of motion is commonly referred to as action and reaction law. And it simply said that for every action, there is always equal and opposite reaction, which means that forces always occur in pairs. Newton's third law of motion, that is action and reaction law, is responsible for rocket propulsion. So rockets are propelled because gases are expelled downward, and when gases are expelled downward because of action and reaction law, the reaction that comes from gases being expelled downward, it is what propel rocket. For example, so when you have a rocket this way, so because gases are propelled or gases are burnt downward, the reaction that comes from that moves the rocket upward. Then also we have recoil velocity of gun. So when you have a gun this way and then a bullet comes out, when the bullet goes forward, the reaction that comes from that is force of equal magnitude but opposite direction, makes the gun to go backward, and that is known as recoil velocity of a gun. So that is Newton's third law. Now, in a separate video, we are going to look at linear momentum as a case study. But in this video, one aspect of Newton's law that I want us to consider is apparent weight in a lift. When you are in a lift, because of action and reaction forces, objects in a lift always have an apparent weight. And this is what I mean. Let's say this is the cabin of a lift, and you have a measuring scale here, graduated in Newton, and you are standing on this scale. Now, there are about 4 scenarios that can be possible when we have a motion in the lift. So let's say this is the cord of the lift, and then the tension in that cord, of course, is going to be upward, so we call it T. As I said before, there are about 4 cases. So let's consider the first case when the lift is stationary. So when the lift is stationary, what happens is that the tension in this cord, which will be the reading in the scale, will be equal to the weight. And we know that weight is always acting downward. So we have 2 forces now that are equal but opposite in direction, according to Newton's third law. So when you are in a lift and the lift is stationary, that is, the acceleration is equal to 0, the weight must always equal to the tension, and it is the tension in the rope that is recorded as the weight of an object standing on the scale. So when you are stationary, tension is equal to weight, that is equal to mass and gravity. Now, what of a case when the lift is going upward? So let's consider upward motion. All right. So when you are in a lift and the lift is going upward at a particular acceleration, we have 2 forces. We have an upward force, which is the tension, and we have a downward force, which is the weight. Because the lift is going upward, the resultant of those 2 forces is going to be equal to tension minus weight, because the tension is greater than the weight for it to go upward. Note that the resultant of forces must equal to mass times acceleration, according to Newton's second law. So it means then that tension minus weight is equal to ma. Then we can say that tension is equal to ma plus weight. We add the weight to both sides. Then we can say that ma plus weight is equal to mg. That means that the tension in the spring is equal to A plus B. So this is the formula that you are going to use to calculate the tension in the rope or the reading in the scale, right? As I said before, the tension in the rope is equal to the reading in the scale. So for upward motion, the tension is equal to mass multiplied by the sum of acceleration of the lift plus acceleration due to gravity. What it then means is that in an upward motion, the apparent weight is going to be greater than the real weight of the object. So that is for upward motion. Now let's see for downward motion. So what if the lift is coming downward? Right, for downward motion, the resultant of the 2 forces that we have, the upward force and the downward force, is going to be equal to weight minus tension. Because when you are coming downward, it means that the weight is greater than the tension in the spring. So it's going to be weight minus tension. That means weight minus tension must be equal to ma, right, according to Newton's second law. Then if you make tension subject of formula and we rearrange, we have weight minus ma, which is equal to mg minus ma. Then that will be equal to m into g minus a. So this is the formula you use to find the tension for the downward motion. So in the downward motion, it means that the apparent weight will be lesser than the real weight of the object. So the last scenario is when the lift is falling freely. So free fall. So what does the free fall will mean? Free fall will mean that the tension or the rope cuts off, and then the lift is coming down at an acceleration which is equal to acceleration due to gravity. That is the free fall. So when the rope cuts off and the lift itself is falling down under gravity. So when it's falling under gravity, what they are going to experience is called weightlessness. That is, when you are standing on the scale is going to measure a weight of 0 Newton because it's falling under gravity. Remember that, let's say we take it to be falling downward, the resultant of the two forces is going to be weight minus tension. And that means weight minus tension is equal to ME. Alright? Then the reading of the scale, T will be weight minus MA, which is mg minus me. Then we have T equal to M into G minus A. Now, because G is equal to A, so we can write it as T is equal to M into A minus A because they are equal. Then A minus A is 0. Tension then becomes mass times 0, which is equal to 0 Newton. So when you have a lift coming down and it's falling under gravity, you are going to experience weightlessness, and then the tension in the string is equal to 0 Newton. So let's take a practice question for us to enrich our understanding. We have a question that says that an object of mass 4 kg is suspended from a spring balance attached to the ceiling of a lift. Okay, so we should put that into picture. So let's draw a diagram. So let's say this is the spring, and then this is the object that is attached. We have the mass of the object to be equal to 4 kg, right? If the spring balance is calibrated in SI unit of Newton, right? So we have the spring balance being Newton. That means the tension in the string is measured in Newton, right? What will be the reading on the balance when the lift is stationary? The first case, question A, is when it is stationary. When it is stationary, acceleration is equal to 0. So even if we say that tension minus weight is equal to ME, we have that acceleration is equal to 0. So tension minus weight is equal to 0, then tension will be equal to weight, and that is equal to mg. The mass is 4. I'll take g to be equal to 10. That is equal to 40 Newton. So the answer to this is equal to 40 Newton. So the reading on this scale, that spring balance, when it is stationary, is equal to 40 Newton. Now the second question is, the lift is moving upward with an acceleration of 0.15 meters per second squared. Right, so we have upward acceleration. As I said before, for upward acceleration, we have tension to equal to M into A plus G. Right? So mass is 4, acceleration is 0.15 plus 10. So we have 4 into 10.15, which is going to equal to 4 times 10.15. And 4 times 10.15 is equal to 40.6 Newton. So when it is accelerating upward, we have an apparent weight of 40.6 Newton. As you can see, it is greater than the real weight. Now the third question is, the lift cable breaks and falls freely with an acceleration due to gravity. So as I said before, when it is falling freely, it is going to be falling under weightlessness, and then the tension is going to be equal to 0 Newton. So in this case, it's going to be very Newton. Then for the fourth one, we have that it is accelerating downwards at 0.15 meters per second. So this is downward motion down. Then T equals M into G minus A in this case. So this is going to be equal to, the mass is 4. We have 10 minus 0.15, which will give 4 multiplied by 10 minus 0.15 is 9.85. So 4 times 9.85 is going to give us 39.4 Newton. So downward acceleration of the lift, the tension or the reading on the scale is 39.4 Newton. Right? So this is how you solve questions like this when Newton's law is concerned.